So today we're covering sections of chapter P. So P stands for probability in the book, and we're just covering parts of P1 and parts of P4, which is why that handout that I sent out to everybody is going to be especially important, because pretty much if you use that, then you're going to know the parts of those sections that I'm going to want you to know. And I kind of tried to write up that handout almost to replace reading the textbook. So you don't necessarily need to read the textbook for this section unless you want a little backup or extra examples or things like that to look at. And the reason why we talk about probability is because most of the foundation of statistics is based on probability. So if we use a random method to select our sample, that means that the laws of probability are going to govern the behavior of that sample. And if you think, as we talked about chapter 4 and we talked about p-values, a p-value is a probability. So understanding the basics of probability and how to compute probability are really helpful in understanding a lot of the other aspects of statistics. So just some basic definitions first, going along with probability. Probability is the proportion of times that an outcome would occur in a very long series of repetitions. So if we did something lots and lots of times and we counted the number of times a particular outcome occurred, we could figure out the probability. When we talk about the sample space is the set of all possible outcomes. So for example, if we're talking about flipping a coin, then the sample space would be heads and tails, because those are the possible outcomes you can get when flipping a coin. If we're talking about rolling a die, one die, then the sample space would be 1, 2, 3, 4, 5, 6, okay, because those are the possible number of dots that can come up when you roll one die. An event is any outcome or set of outcomes in a sample space. So if we're talking about rolling a die, an outcome could be rolling the number 6, or an event could also be rolling an odd number. So rolling an odd number would encompass multiple outcomes. And the notation that we're going to use for probability is a capital P with parentheses here. And in the parentheses, you write whatever it is you're looking for the probability of. So for example, if you want to know the probability of flipping heads, then you'd put P, and then in parentheses, you put heads and whatever that's equal to. So of course, probability of flipping heads is about 50-50, so 0.50. And our exam is going to be in Blackboard again in the Respondus. So it's going to be a little bit harder for me to test you on notation, but I do really recommend using the correct notation when you're writing things down. And definitely in your homework, when you're doing those probability problems, if you just write an answer, I'm not going to give you credit for that. Like I want to see things written out. I want to see the process. I want to see how you got to that answer. I don't want to just see a number at the end. And writing the notation along with it will help you understand what it is you're doing and how you arrived at that final answer. So, and I'll show you what that looks like as we go along today. When we think about an event, we're going to be interested in whether that event happens or doesn't happen. So it's going to be something that's either true or not true, happens or doesn't happen. So for example, a randomly selected card is a heart. That could be an event. Or our response variable being greater than 90, that could be an event. Or a randomly selected person is male, okay, that could be an event. Or it rains today, that could be an event as well. And probably will rain today. At least it says it's going to, but it said that yesterday and I felt like it didn't rain a lot yesterday. If we're talking about finding probability, if all the possible outcomes are equally likely, then we can figure out the probability of an event by taking the number of outcomes that are in the event that we're interested in and dividing by the total number of outcomes. So for example, let's say we're drawing a card from a standard 52 card deck, and we want to know, what's the probability that I would draw a jack? Well, there are 4 jacks in a 52 card deck. All the cards should be equally likely. So the probability of drawing a jack would be 4 out of 52, or in other words, 1 out of 13. And I should have put this on this slide, but I guess I didn't. But pretty much in our class, when we give the answer for probability, it's going to be in decimal form. So for this one here, that's going to be 0.0769. And my general rule is you have to use at least 3 decimal places, and I prefer 3 values beyond the leading zeros in general. So you have to use at least 3, and it's a good idea to use 3 beyond the leading zero numbers. All right, so let's talk about just the basic probability rules. So first of all probabilities are numbers between 0 and 1. That kind of corresponds to 0% to 100%, which makes sense, right? Because you can't have a more than 100% chance of something happening, and you can't have a less than 0% chance of something happening. If we look at the probability of all possible outcomes, so basically we add the probability for everything in the sample space, then it should always add up to 1. So there's not going to be any like holes or anything like that. So always adds up to 1 or 100%. The next rule is called the complement rule, and it says that the probability that an event does not occur is 1 minus the probability that it does occur. So if I want to know the probability that A does not happen, I can just take 1 minus the probability that it does happen. So here's a little example. If I'm rolling 1 die and I want to know the probability that I do not roll a 6, then it's just 1 minus the probability that I do roll a 6. And when you roll a die, all the sides, as long as you don't have a loaded die, are equally likely. So that would, the probability of rolling a 6 would be 1 out of 6. So 1 minus 1/6 gives me 5 6 or 0.8333. So the probability that I do not roll a 6 would be 0.83333. All right, okay, just notice like the notation that we're using in here. So the big P with the parentheses, that tells you what we're finding the probability of. And notice how I've written out all the steps here, which led me to my answer. So I don't just have like a number answer, I have the steps that led me to the answer. Okay, the next rule is called the additive rule. And it says that if 2 events are disjoint, so there's another term that you might want to learn. And disjoint means that they have no outcomes in common. So they're mutually exclusive. So if 2 events are disjoint, the probability that one or the other occurs is the sum of their individual probabilities. So something to note is that when we're going to use the additive rule, one of the key words to know that we're going to use the additive rule is this word or. Okay, if I want to know the probability of A or B occurring, then I'm going to use the additive rule. So let's think a little bit more about what disjoint events mean. So we said they're disjoint or they're mutually exclusive if only one of the 2 events can happen at the same time. So for example, if I'm rolling a dice, then rolling a 1 and rolling a 6 would be disjoint, right? I can't roll a 1 and a 6 at the same time on only 1 dice. So those are mutually exclusive. They're disjoint. On the other hand, rolling a 1 and rolling an odd number are not disjoint because it's possible that I could roll a 1 and roll an odd number at the same time. So those would not be disjoint and not be mutually exclusive. So the additive rule that we're going to talk about in our class is only for the case of disjoint events. Your book does talk about what to do when they're not disjoint, but I'm not going to require you to do problems like that on the exam or anything. So just the disjoint version of the additive rule is what we're talking about in here. So here's the additive rule. If I want to know the probability that A or B occurs, then I can just add their individual probabilities. So if I want to know the probability of rolling a 6 or a 2, that's just the probability of a 6 plus the probability of a 2. And since the probability of a 6 is 1/6 and the probability of a 2 is 1/6, I could add those together and that probability would be 0.33333 repeating. All right, and the last rule we're going to talk about is called the multiplicative rule. And the multiplicative rule has two parts, and we are going to learn two parts to this one. So we have the multiplicative rule when events are not independent, and we have the multiplicative rule when events are independent. So when events are not independent, then the probability that both events occur is the probability of the first event times the probability of the second event, given that the first event occurs. So we write that out like this. So the probability of A and B occurring is going to be the probability of A times the probability of B if A. This is one of the ways that we write that out. So this means the probability of B occurring given that A already occurred, basically. And notice the keywords that go along with the multiplicative rule are and. We're looking for and. So in the problem, you might see words like both occurring or something like that, or this and this occurring. So and is a keyword for the multiplicative rule. If the events are independent, then it makes it easier. We don't have to worry about what happened on the first time. We can just multiply the two probabilities together. So probability of A times probability of B. When we talk about events being independent, then what we mean is that the outcome of event the first time doesn't affect the outcome of the second event. So for example, when we look at rolling a die, if I roll the number 6, then that is not going to affect what I get the next time I roll the dice, because each roll of the dice is independent. So, so those are independent events. But if I think about a deck of cards and I'm drawing cards from the deck, if I draw the King of Hearts, the first draw, and I'm still holding that card, I don't replace it, and I draw another card, well, whatever I drew the first time is going to affect the probability of what I draw the second time, because it changes the ratio of everything that's left in the deck. So that would be an example of where they are not independent. And that's when we have to look at this conditional probability. So we talked about that being, we have to figure out the probability of something occurring if the other event already occurred. So in this case, the probability of A if B is the probability of A if we know that B has already happened. So there's different ways to kind of read that or say that. We might say the probability of A if B, the probability of A given B, the probability of A conditional on B, and when we write it out, and this is how I often write it because this is how I learned probability, you might see it written as PA and then like a big vertical line and then B. So the big vertical line means like given that B occurred, basically. So these are all different ways to say the same thing here. Okay, so now we're going to start looking at some examples and see if we can apply the probability rules to these examples. And this is the part where it's really sad that we're not in class physically together, because you can't really have a good probability lesson without candy involved. And I always bring M&Ms or Skittles or some kind of candy to do a probability lesson. But unfortunately, there was no way for me to virtually give you guys all candy. So we're just going to have to rely on some past data that was collected, and it's going to be a lot less delicious this way. But this is some data that I had my kids collect on peanut butter M&M distribution. So we all took samples of peanut butter M&Ms and we counted up the different colors in the sample of M&Ms. And based on this sample, we're trying to figure out what the distribution of colors is in peanut butter M&Ms. So first question is, what's the probability that a randomly selected M&M would be yellow? All right, and my chart gives both the counts that we got, and then it converted those counts into a percentage already as well. So for example, if I look at yellow here, since that's the one I'm interested in, if I take that 27 divided by 122, then I would get my proportion of 0.221. So this one really is just as simple as reading the chart. So the probability of, if all these M&Ms were in a big giant glass bowl and somebody reached their hand in and grabbed one out, the probability of getting a yellow would be 0.221. All right, let's get a little trickier here. Now let's figure out the probability that a randomly selected M&M would be either red or green. So what's the key word in this question that's going to help us figure out which rule we should use? Or, exactly, or either. Both of those are good ones. Okay, so when we see the word or, which rule are we going to use? What's the name of the rule that we're going to use? The additive rule, exactly. So I'm looking for the probability of red or green. And if I'm just drawing one M&M out, there's no way I could get red and green at the same time, right? I either get red or green. So these events are disjoint. So in order to figure out the probability, I'm going to take the probability of red plus the probability of green. So if I look at my chart here, red was 0.270 and green was 0.115. So I'll take 0.270 plus 0.115 and I get 0.385. So that's the probability of getting either a red or a green if I draw one M&M at random. All right, let's look at another one. Now we're drawing one M&M out at random again. What's the probability that the randomly selected M&M is not blue? Okay, so what's the key word in this one? It's going to help us figure out which rule we're going to use. Not, exactly. So we're going to use the complement rule. So the complement rule says the probability that something does not occur. So in this case, the probability of not blue is 1 minus the probability that it does occur. So in this case, 1 minus the probability that we do get blue. So here I'm going to take probability of blue was 0.066. So probability of not blue is 1 minus 0.066, which is 0.934. All right, let's look at another one here. What's the probability that a randomly selected M&M is not either brown or orange? All right, so this one's got multiple keywords here. We're going to have to combine some of the rules to figure this out. So not and or. So we're going to end up using the complement rule and the additive rule. So if I want to know the probability that something does not occur, so the probability of not brown or orange, then that's 1 minus the probability that it does occur. So I'm going to say 1 minus the probability of brown or orange. All right, and then if I want to figure out the probability of brown or orange, I'm going to use the additive rule. So I'll have 1 minus, and then the probability of brown plus the probability of orange. Okay, I'm going to do all that math before I subtract it from 1. So I'll end up having 1 minus, well, brown was 0.238. And orange is 0.090. I'm going to run out of room here. So if I add those two together first, 0.238 plus 0.090, I get 0.328. Now I'm going to subtract that from 1. And I'll finally get my answer as 0.672. So the probability that I take a randomly selected candy out of my bowl, the probability that's not brown or orange is 0.672. Let's look at a card example now. Suppose we draw 2 cards from a standard deck without replacement. What's the probability that both cards are hearts? So this time we're drawing 2 cards and we want to know the probability that they are both hearts. So that's a multiplicative rule kind of thing. And if we're drawing the 2 cards without replacement, that means we're talking about the multiplicative rule when the events are not independent. So I'm looking for the probability of a heart the first time and a heart the second time. And these are not independent because once I draw the first card, then it's going to affect the probability of everything else. So looking at this, we're going to take the probability of a heart the first time times the probability of a heart on the second draw, given that we got a heart on the first draw. So let's look at how we're going to calculate those. So let's start with a heart on the first draw. So on the first draw, there's 52 total cards in the deck. All the cards are there. And hearts, there's going to be 13 hearts because there's 13 of each of the 4 suites that are in a standard deck. So the probability of drawing a heart on the first draw is 13 out of 52. All right, now let's say we drew a heart the first time. Now we're holding it in our hand. We're going to reach into the deck and draw another card out. Now that we've already got a heart on the first time, how many hearts are left in the deck? So before I drew any, there was 13. I drew one of those hearts out. I'm holding on to it. So now there's 12 hearts left in the deck, right? So 12 hearts left. And how many total cards are left in the deck? 51. So the probability of getting a heart the second time, given that we got a heart the first time, is 12 out of 51. So now I just have to multiply these things together. And you could multiply, you could do it however you want because it's a multiplication problem. So you can multiply the numerators and the denominators, then divide, or you can multiply each of these individual values and then multiply those together. So I think that's what I'm going to do. So I'm going to take 13 over 52, which is 0.250. Because remember when we started with a fresh deck, a quarter of the deck was hearts. And then if I take 12 divided by 51, then I get 0.23529. And if I multiply those together, then I get 0.0588. All right, so let's look at another one. So we're still going to be drawing from the deck here. This time we want to know the probability that the first card drawn is a heart and the second card drawn is a diamond. So this time we're looking at a heart the first time and a diamond the second time. So this is still a multiplicative rule that we're going to use because we have and here, and these events are still not independent. So that probability is going to be the probability of a heart the first time times the probability of a diamond the second draw, given that we got a heart the first time. So probability of drawing a heart the first time, that's the same as we did in the last problem. So that's just 13 out of 52. Okay, so now imagine we draw a card, it's a heart, we're holding on to the heart. Now we're going to reach our hand back into the deck. How many diamonds are in the deck knowing that we drew a heart the first time? Yep, 13. And then how many total cards are in the deck now that we drew a heart the first time? 51. So now we multiply those together. So that's 0.25 times 0.255, which gives me 0.0637. Okay, so now let's say we're going to draw 5 cards from the standard deck without replacement. What's the probability of all 5 cards being black? So same idea, using that multiplicative rule when we have not independent events. See if you can figure it out. I'll give you a second. All right, so basically how we would do this problem, same as we did the other one. We start with our fresh deck of cards. In a fresh deck of cards, half the cards are black and half are red. So that means that the probability of drawing a black on the very first draw would just be 26 out of 52. Now, if I draw black the first time, when I reach my hand in the second time, there's only going to be 25 blacks, and there's only going to be 51 cards. So the probability of a black the second time, given that I got a black the first time, is going to be 25 out of 51. Now, when I draw my hand in or put my hand in again the third time, now there's only 24 blacks in the deck because I'm already holding 2 in my hand. And there's only 50 cards left in the deck, so I would take 24 over 50. And you can kind of see the pattern here. So the next one would be 23 over 49. And for the fifth card, we would have 22 over 48. So if I multiply all those together, then I end up with the 0.0253. Don't you love probability problems? They're kind of like a little puzzle, and you can just have to figure it out. Which rules can I use? How can I solve this puzzle? All right, let's talk about the multiplication rule now when we have independent events. So when we have independent events, it's actually a lot easier because we don't have to worry about what happened the first time or the second time. We just have to, we can just multiply everything together. So here's an example. Suppose that a set of 3 traffic lights along one section of road operate independently. Since this is a fairly main road, the lights are green with probability of 0.7 and red with probability of 0.3. What's the probability that all 3 lights are green? Okay, so keywords here, we're looking at independent, and we want to know the probability of all 3 lights being green. So that would be the probability of the first light being green, and the second light being green, and the third light being green. But because these are independent, then I can just multiply the probability of green light together, basically 3 times. And I don't have to worry about what the first light did or the second light did because they're independent. So the probability of a green light in this one was 0.7. So I'll take 0.7 times 0.7 times 0.7. And that tells me the probability that all 3 lights would be green. All right, so when they're independent, then we don't have to worry about what happened the time before. We can just take that probability and multiply it together. All right, so let's look at one more example here. Oh, just kidding. I didn't put the other example on my slideshow. So I'll just tell you what it is. It's in your notes too. So we'll do it down here. So the second example is, what's the probability that the first 2 lights are green, but the third light is red? So we're basically looking for the probability of a green, and a red. Really, I should say and in between those. All right, so probability of a green, and a red is going to be the probability of green the first light times the probability of green the second light times the probability of red on the third light. Okay, but again, they're all independent, so you don't have to worry about what happened the time before. You just take the probability of green lights times the probability of red light, and you'll get your answer. So go ahead and work on that, see what you get. All right, perfect. Everybody got it like all at once. So we're going to take 0.7 times 0.7 times 0.3, and that's going to give us the 0.147. Perfect. All right, so now I want you guys to practice using those probability rules to answer some probability questions. So the second thing that I had wanted you to print out for today was this probability practice problems worksheet. It looks like this, and it has all the serial names at the top. So you know you got the right one if it's got the serial problem at the top. So I want you to take a second and work on problem 1. If you finish problem 1, go ahead and work on problem 2. All right, let's go ahead and take a look at what we got here. I'll pull up the answer key here so you can see the answer. So the first one, what's the probability that a cereal sold as a brand other than the Big 4? So remember, one of our probability rules says that if I add up the probability of everything in the sample space, it has to add up to 1. So if I remember that, then if I add up everything else and subtract that from 1, that's going to tell me what the missing number is. So in this case, we ended up with 0.146. Second one, what's the probability the cereal sold is not Kellogg's? So the probability that it's not Kellogg's would be 1 minus the probability that it is Kellogg's. So in this case, the probability of Kellogg's was 0.301. So 1 minus 0.301 gives us 0.699. The probability of cereal sold is Post or Quaker. So or being the key word, telling us we're going to use that additive rule. And as far as I know, a cereal being Post or Quaker is disjoint. Like you can't have a cereal box that's both Post and Quaker at the same time. So we can just add those individuals' probabilities together. So probability of Post plus the probability of Quaker gives us that 0.254. And then if two cereals are sold independently, so independently is a key word to watch for. What's the probability that both cereals are General Mills? So the probability of General Mills and General Mills. And since they're independent, we can just take that probability, the 0.299, and multiply it together twice for each cereal and get the 0.0894. So how'd everybody do? How'd everybody do on problem one? You most of them right? Thumbs up. All right, did you guys make it to problem two? Work on the Halloween candy one. So the Halloween candy one, we've got counts here. Ryder comes home with 6 Milky Ways, 4 Snickers, 5 Dum Dums, 2 Reese's, 3 Skittles, and 5 M&Ms. And Ryder's sister Kendall sneaks her hand into the bag and pulls out 1 candy. What's the probability it's a Milky Way? Well, if you add those numbers, 6, 4, 5, 2, 3, and 5, then you end up with 25. So there's 25 total candies in the bag. 6 of them were Milky Way. So the probability of Milky Way would be 6 out of 25, which is 0.24. What's the probability that the candy is chocolate? Looking at my list here, Milky Way, Snickers, Reese's, and M&Ms are all chocolate. So we can add all those probabilities together and you get 0.68. And then probably the trickiest one here was part C. Suppose Kendall grabs 2 candies instead of 1. What's the probability that both candies are Snickers? So we're talking about 25 candies in the bag. It's a fixed number. So these are not independent events, since whatever she draws out the first time is going to affect the probability of what she draws out the second time. So the first time, with the first candy, there's 4 Snickers out of the 25 total candies in the bag. The second time, she's already eaten one of the Snickers, so there's only 3 Snickers left out of 24 candies left. So multiply those together and you get the 0.02. So next we're going to look at kind of combining a bunch of the rules together in this little example. And I'm just going to warn you up front that this example is going to seem pretty confusing and you're going to be like, man, I hope we don't have many of those in my homework. Don't worry, this is all kind of like leading up to an easier way. So I'll kind of give you a spoiler there. So suppose that the proportion of left-handed people in the population is 0.10. And suppose we randomly select 3 people from the population. What's the probability that exactly 1 of the 3 people is left-handed? So to figure out this probability, the first thing we would need to do is figure out how many ways we can get 1 left-handed person in a selection of 3 people. So if you think, okay, well, I have 3 people that I'm looking at here. So 1, 2, 3. Okay, it could be that the first person is left-handed and the other 2 are right-handed. So I could get a lefty, righty, righty. Or I could get a right-handed person first, then the left-handed person, then the right-handed person. So I could be righty, lefty, righty. Or I could be righty, righty, lefty. Okay, so there's 3 ways that I can get 1 left-handed person in a selection of 3 people. All right, so basically, if I'm trying to figure out the probability that I get exactly 1 lefty in a sample of 3 people, then that is going to be the probability of getting a lefty, righty, righty, or a righty, lefty, righty, or a righty, righty, lefty. Okay, I'm just looking at those 3. Remember those 3 possible ways to get 1 lefty out of 3 people. So this is an or kind of probability here. And we all know that the keyword or goes with the additive rule. So I could add those together. So the probability of lefty, righty, righty, plus the probability of righty, lefty, righty, plus the probability of righty, righty, lefty. All right, so now how do we figure out this part? The probability of a lefty, righty, and righty. Well, in order to do that, we're going to use the multiplicative rule for independent events, because when we're drawing these people from the population, they're essentially independent, because the population is so huge that it really doesn't, taking one person out of a population of millions of people really doesn't affect the probabilities. All right, so let's start with the first one. The probability of a lefty, righty, righty would be the probability of a lefty times the probability of a righty times the probability of a righty. So I'm going to get 0.1 times 0.9 times 0.9, which is 0.081. And the probability of a righty, lefty, righty is probability of a righty times the probability of a lefty times the probability of a righty. So that's 0.9 times 0.1 times 0.9. So that's 0.081. Okay, similar idea for righty, righty, lefty. I get 0.081. So what do you notice about all these values over here? They're all the same, right? They're all the same. So really what I could have done is just looked and said, okay, I have one lefty in my group. So let's take the probability of a lefty, take one of those, and I have two righties in my group here. So let's do 0.9 times 0.9, which would just be 0.9 squared. Okay, and one lefty, so that's just 0.1 to the 1 power. Okay, so I could figure out that probability, and then I have that 3 times for the number of ways that I was able to get one lefty out of 3 people. So I could just multiply that by 3, and that would be a little bit simpler way to get my answer, because now I'm going to add all those up here to come up with my answer. So that all seems really complex, like I said, and there is a better way, and we're going to kind of talk about what that better way is. But that better way is actually just, like I said, it's derived from using these same probability rules that we just talked about. So to help us get in with the new and better way that we're going to like, there's a lot of notation that you have to keep track of. So N is going to be the number of trials. So in my lefty, righty, righty example, there was 3 people that we were drawing from the population. So my number of trials was 3. K is the number of successes. And by success, we mean whatever it is that we're interested in. So in this case, we're calling a success a lefty because that is what I was interested in. So I wanted to know the probability of 1 lefty out of 3 people. So the number of successes is 1 because I wanted to know 1 lefty out of 3. So if there's 1 success, then I could just take the number of trials minus the number of successes, and that tells me how many failures there are. So in this case, a failure is a righty. So we would have 3 minus 1, which is 2. So there's 2 failures. P is going to be my probability of success. So in this case, because my success was a lefty, my probability of success is 0.10. And then if the probability of success is 0.10, then the probability of failure is going to be the complement to that. So it's going to be 1 minus 0.10 in this, for this example, which is 0.90. Okay, so again, then based on that, this is kind of what I was showing you on the other slide here. We're going to be able to figure out the answer to this, so the probability of getting exactly K successes in N trials. So I can just take the probability of success, which was 0.1, raise it to the power of however many successes I had. I can multiply that by the probability of failure. So in this case, that was the righty. So that's 0.9 raised to however many failures I had. So in this case, it was 2. And then I multiply all that by the number of ways to get exactly K successes in N trials. So for the example I was working on, that was 3. But how would I figure this out in general? How would I figure out how to count the number of ways to get exactly K successes in N trials? Well, when we did it for this example, we just made a list of all the possible outcomes, right? We said, oh, okay, there's 3. You know, I want 1 success, so I could have lefty, righty, 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 lefty, righty, 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 lefty. So I made a list, which works great when we don't have that many, okay? But what if I wanted to figure out the number of ways that you could have, I don't know, let's say 10 successes out of 100 trials. Well, then that would be a lot of R's and L's written out over and over again to try to figure out all the different possible ways you could do that. So we're going to learn a new way to count. I know you thought you learned how to count in kindergarten, but in our class, college, yay, you get to learn how to count. And to help us learn how to count, we're going to use something called factorials. And you may or may not have learned about factorials in another class before. The factorial sign is an exclamation point. So when something has a number with an exclamation point, we read the exclamation point as factorial. So this is n factorial. And n factorial is just equal to the value, and then you multiply it by all the integers that are less than that value. So for example, if I wanted to do 5 factorial, then 5 factorial is 5 times 4 times 3 times 2 times 1. Okay, so I just start with the number and then I subtract one integer each time and multiply it until I get down to 1. So try multiplying this out on your calculator, 5 times 4 times 3 times 2 times 1, and tell me what you get. 120, perfect. Okay, so you should have all gotten 120 when you multiplied that out. Now there is a button on your calculator, if you have a scientific calculator, that will do all that computation for you. I mean, when we did it for 5, no big deal. But if you're doing something like, I don't know, 25 factorial, it would get a little tedious multiplying all those numbers together. So fortunately, your calculator can do this for you. So let's see if we can find the factorial button on your calculator. So Casio and TI, those are the most common ones that I see. So I've got pictures here to help you find it. And if you have something else, I can still help you find it. Okay, so on the Casio, then you're looking for the X exclamation point, which on my Casio, which is the one pictured here, is right above the X to the -1 key. So in order to access that factorial, what you do is in your calculator, you would put 5, and then you click Shift, and then you click that X to the -1 key. So try putting in 5, Shift, and then you hit the X to the -1, which is really the X factorial, and then hit equals, and you should get 120. All right, now if you have a TI, and most of the TIs that I've seen work this way, then what you're looking for is a probability button on your calculator, and it's going to have a little menu in it. So look for something that says prob or PRB. Okay, so on the TI, you're going to click your 5 first, just like you did before. Okay, then you're going to click your probability button, and then it's going to bring up a menu, and one of those is going to be the exclamation point, the factorial, and so you're going to click whichever one it goes to. I don't have a TI, so I don't have it right in front of me, but I think it's like option 3 or 4, something like that. Maybe it's even option 1. So you're going to look for wherever the exclamation point is, and then you'll hit equals, and you should also get 120. Doing factorials is super fun, and so we can figure all these out. So what is 4 factorial? Try that on your calculator, see what you get. 24, yeah, so 4 factorial is 24. So now you should be able to do like any factorial. So I'm not going to give us time to work on number 3, A and B. That has some more factorials on it on the probability practice problems. So I'll skip over those. All right. So these factorials, what they're going to help us with is the counting. Remember, we talked about how we wanted to be able to learn how to count. To count like the number of ways to get exactly K successes in N trials, we can use something called combinatorics, which uses this binomial coefficient. Okay, so most of the time I'll probably refer to this as a combination. You might have heard of combinations in your other classes. Sometimes they go along with permutations, which is similar but different. We're only going to talk about combinations in our class. But basically, if I want to count the number of ways that I can get exactly K successes in N trials, then I can use this formula right here. So in big parentheses, I put N, the number of trials on top, and K, the number of successes on the bottom. Okay, so I put those in big parentheses. And the way that we read this is n choose k. Okay, so that's when I talk about it, I'm going to say n choose k or 10 choose 5, something like that. This is not a fraction. Okay, so I just want to repeat, this is not a fraction. There is no fraction line in the middle of this. You do not divide the n and the k to get the right answer. Okay, this is the notation for combinations, and it's read as n choose k. And what this is equal to is n factorial over k factorial times n minus k factorial. Okay, so if I wanted to know the probability of 2 successes in 5 trials, okay, then that would be written out like this. So I'd have 5 factorial over 2 factorial, and then 5 minus 2 is 3, so then I would have 3 factorial. So I could plug those numbers in, like the 5 factorial divided by 2 factorial times 3 factorial. But if you try a few numbers for factorials, like put in 100 factorial on your calculator, and you'll probably get an error. I do. Mine says, it's like too hard. I can't do that. Forget it. I'm not going to do it. So one way that you can kind of get around that, if you just have your factorial button, is this. Look at this trick. Okay, so I have 2 tricks. This is the first trick. So for this trick, if I think about what 5 factorial, 2 factorial, and 3 factorial mean, 5 factorial is 5 times 4 times 3 times 2 times 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. So now I've got this fraction here. And because everything is multiplied together, I can cross out similar terms. So look, I can see there's a 3 in the top and bottom. There's a 2 in the top and bottom. There's a 1 in the top and bottom. So those will all cancel. And then I can just multiply these numbers to get the answer. So I would have 20 divided by 2, which gives me the 10. So that's one way we could do it when we have really big numbers. The 5 factorial won't be a problem, but big numbers would be a problem. Okay, or there's another cool button on your calculator. All right, so if you have the Casio, if you have my exact Casio, then it's going to be on the division key. Okay, there's a little thing above it that says NCR. So that's kind of what you're looking for, is an NCR button somewhere on your calculator, especially if you don't have one of these too. If you have a TI calculator, then it should have been in that same probability menu where you found the factorial. Then there should have been like a little NCR inside of there. All right, so we're going to try the one we just did, the 5 choose 2. Okay, so to do that on your calculator, you're going to put in 5. Then you have to hit the NCR button. So you might have to hit Shift and then the NCR, and then you're going to type in 2 and then equals. So you're going to type in 5, then however you get the NCR button to press, do that, then hit 2, then hit equals. All right, and you should get the 10. Okay, and this is what it looks like on my calculator when I type it in. When I click the NCR button, then it puts like a little C there. So it says 5C2, which is like 5 choose 2. So let's look at a couple other ones here just to see if we can get it. So you don't have to write it all out like this if you have the NCR button, which most of you should have it. If you have a scientific calculator, you should have an NCR button. So let's try this 10 choose 8 right here. So try putting 10 choose 8 into your calculator, and let's see what you get. 45, perfect. Okay, and try the 7 choose 2, and then I'll feel like we are masters at this. 21, excellent. Okay, now you're ready to finally learn the actual formula that we're going to use to figure out these probabilities here. So if I want to figure out the probability of getting exactly k successes in n trials, then here's the formula that I'm going to use. Okay, we're going to do n choose k. That's going to tell me the number of ways to get k successes in n trials. And I multiply that by the probability of success raised to the number of successes times the probability of failure raised to the number of failures. So notice that there's basically 3 things here. There's n, there's k, and there's p. So looking at these problems, if you can just figure out those 3 things, you can plug them all in and you'll be good as gold. So this one is pretty basic. They don't even put it into a word problem for us. So we know we have n is equal to 8. We know P is equal to 0.3, and this is the notation here. They're telling us that K is equal to 6. So we can get that if we look back up here. We're looking for the probability that X is equal to K. So K is the thing that they're saying X is equal to here. All right, so remember, here's our formula. So let's just plug all these numbers in and see if we can work this out. So first I have N choose K. So that's going to be 8 choose 6. So I have 8 choose 6 times P to the K. So 0.3 to the 6th power times 1 minus P. So that's 1 minus 0.3 to the N minus K. So 8 minus 6 in this case. Okay, and the easiest thing to do before you start plugging numbers in your calculator is to do this, is to simplify the stuff that would be in parentheses so that you don't have to use parentheses on your calculator. It's like one less mistake you might make on your calculator, basically. So if I do that, I get 8 choose 6, and then I get 0.3 to the 6th times 0.7 squared. Okay, so all I did is I took the 1 minus 0.3 and I did that calculation. I got 0.7. And I did the 8 minus 6, and I got a 2. All right, now we're going to plug this in our calculator. So you can plug it all in one like big old line, and depending on your calculator, then you might get some good results out of that. But the way that I recommend doing it is doing it piece by piece, but adding on. So essentially, I'm going to do the first part here, and then I'm going to hit equals. Then I'm going to hit times so that it uses this answer and then multiplies it by the second part. And then I'm going to hit times again and do the last part and hit equals, and then it should end up with the right answer. So let's do this one all together, okay? Okay, so starting with the first part, I'm going to do 8 choose 6. So on your calculator, do 8 choose 6 and then hit equals. Okay, so far, my calculator says 28. So I did 8 choose 6 and I got 28. Okay, now I'm going to say times. Okay, and notice that that's going to take the answer, the 28 that I already got, and multiply it by what I'm going to put in next. So I hit times, and now I'm going to go 0.3 raised to the 6th power. All right, this might be another button that you might have to find on your calculator if you haven't used it before. On the Casio, it's this X with the little box by it right here. Okay, so I would put in 0.3, then I hit this little X with the little box by it, and I put in the 6. If you have a TI, it might look like a caret, so like this. So then you would hit 0.3 and then the caret button and the 6. I've seen some calculators that have a button that looks like this, Y to the X. Okay, so all of these are the same thing. They're raising something to a power. Okay, so if you got that far, then hit equals. Okay, and now I have 0.020412. So I'm 2/3 of the way through my problem. Now I'm going to hit the times button again and tack on that 0.7 to the 2. Okay, so I hit times and then I do 0.7 squared or 0.7 raised to the 2nd power. Like this. So I have the previous answer times 0.7 squared. And then I ended up with this number, 0.010000188. So essentially 0.01. So basically the difference between this one and the one we just did is that now it's the same kind of problem, but it's given to you as a word problem. And this is mostly the way that you're going to see it on an exam or something like that, because of course, statistics is all about the word problems. We love word problems. And the only thing different about this is you just have to read the word problem and identify N, K, and P. So this one says, suppose that undergraduate students at a university are equally divided between the 4 class years, freshman, sophomore, junior, and senior, so that the probability of a randomly chosen student being in any one of the years is 0.25. If we randomly select 25 students, what's the probability that exactly 8 are seniors? All right, so remember, I want to identify N, K, and P before I start. And I always do this exact thing. I write down N, K, and P. I figure out what they are, because then after that, it's just plugging numbers in. So N, that's the total number of trials. So that's going to be the 25. I'm randomly selecting the 25 students. Okay, N always has to be greater than or equal to K. That might help. K is going to be the number of successes. So in this case, a senior is a success. So K is going to be 8. And then the probability of any of the years is 0.25. So the probability of a senior is going to be 0.25. So that's going to be my P. All right, so now I'm going to write out my formula here. So I'm looking at the probability that X is equal to 8. And that's going to be N choose K. So that's going to be 25 choose 8 times P, which is 0.25 raised to the 8 times 1 minus 0.25 raised to the 25 minus 8. All right, now I'm just going to simplify this before I plug it into my calculator. I'm going to simplify what I can. So I have 25 choose 8 times 0.25 to the 8 times 0.75, okay, because that's 1 minus 0.25 to the 25 minus 8. And 25 minus 8 is 17. So I end up with 25 choose 8 times 0.25 to the 8 times 0.75 to the 17. All right, now let's plug it all in, okay, piece by piece. So starting with 25 choose 8. So I'm going to do 25, the NCR 8 equals, then I hit times 0.25 raised to the 8th power. And then I'm going to hit equals again. And at this intermediate stage, my number is 16.5-ish something. Okay, now I hit times again. So it should say answer times. And I'm going to do 0.75 raised to the 17th power. And then hit equals again. And this should be your final answer. All right, when I did it, I got 0.124. All right, how'd you guys do? Thumbs up, thumbs down? So this is number 7 on the probability practice problems, and it brings up a point that sometimes people struggle with, which is why I'm going to go over it. So it says, each day the probability of rain on a tropical island is 80%. You're planning a 7-day trip to this island. What is the probability that it will rain every day while you are here, or while you are there? Okay, so remember that we always want to write down N, K, and P before we get started. So I'm going to write down N, K, and P. N is the number of trials. And in this case, we're planning a 7-day trip to the island. So N is 7. K is the number of successes. In this case, a success is rain. And it says it's going to rain every day, which means that the number of successes is also 7. And P then would be the probability of rain, which on this island is 80% or 0.80. All right, so I'm figuring out the probability that X would be equal to 7. So that's going to be 7 choose 7 times 0.80 to the 7th times 1 minus 0.80 to the 7 minus 7. So simplifying that, I get 7 choose 7 times 0.8 to the 7th times 0.20, and 7 minus 7 is just 0, so it's 0.20 to the 0. Okay, so here's what I want to point out, because I get people that mess this up a lot. Anything raised to the 0 power is 1. Sometimes people see the 0 there and they're like, oh, it's a 0, it's nothing, I can just get rid of the 0. So you can't just get rid of the 0, you would get rid of the whole term basically, because the whole term is equal to 1. So what I'm trying to say is that 0.2 to the 0 is not the same as 0.2. Okay, so you can't just get rid of the 0. In fact, 0.2 to the 0 is equal to 1. So it's not equal to 0.2, it's equal to 1. And you'll see that when we plug that into your calculator. So let's plug in each of these things here. So starting with 7 choose 7. So 7 choose 7 is 1 also. And then I multiply that by 0.8 raised to the 7th power. I hit equals and I get 0.2097 with some extra decimals on there. Now I multiply that by 0.2 to the 0 power. Okay, and that's where you see that it's the same number afterwards. So it's just like multiplying by 1. So I end up with 0.2097 as my final answer for that one.